Shall I start?
Yes, ready for me.
Okay, so Nato is ready, and Martin, ready?
Yeah, I'm ready.
Hi, can everybody hear me? Good afternoon, everyone. I think we have more participants streaming in, but I'm not going to let you wait. So let's just start now. So good afternoon and welcome to this third webinar hosted by the Malaysian Water Association and Malaysia International Water Convention. Today's topic is trunk main monitoring in Malaysia. So once again, thank you for joining us. We are pleased to have with us today two NRW experts from Xylem. Our first presenter will be Mr. Martin Shaw, Non-Revenue Water Solution Architect from Xylem Incorporated. Martin has over 25 years experience of working in the field of non-revenue water management in the UK, Australia, and Malaysia. Our second presenter will be Mr. Matthew Kennedy, Project Manager from Xylem, who has been managing multi-million-dollar smart water and analytics projects across Asia and Australasia. So participants, halfway through this webinar, we will run a poll and we will give you 3 questions. So we hope you can participate by answering just 3 short questions. And if you have any questions for our speakers, you can key in your questions anytime during the presentation. And Martin or Matthew will answer all your questions at the end of the webinar. The Q&A icon is located at the bottom bar on your screen. So I hope everybody can find that. And of course, I'm sure you like to watch today's session again, and we will stream this video live on YouTube. So we will provide you all the details at the end of the session. So let's start now. And I would like to invite Yang Bahagia Datuk Engineer Abdul Kadir bin Muhammad Din, President of the Malaysian Water Association, to welcome everyone. Datuk, are you ready?
Yes, thank you, Denise.
Welcome.
Yeah, can I start?
Yep.
Okay, Bismillahirrahmanirrahim. Assalam sejahtera, ladies and gentlemen. Good afternoon and welcome to today's Malaysian Water Association organized webinar series. So this afternoon, the webinar is the third in the series and is entitled Trunk Main Monitoring in Malaysia. Trunk mains are often a water company's most neglected asset despite being of critical importance. I would say the lack of good operation maintenance and standard operating procedure, and coupled with wrong choice of pipe material and poor installation, will worsen the situation, leading to shorter lifespan of the pipes. These trunk mains carry a very large volumes of water, and due to lack of redundancy in the trunk main networks, it will result in pipe failings and affect the supply to large number of customers. Basically, there are 2 main indicators that can help identify if the pipes is vulnerable to bursting or pressure transient and pipe leaks. So for the first portion, the pressure transients are large changes in pressure over a very short time frame, and this is commonly known in the technical jargon called as water hammer. So these pressures changes and can exert significant energy along a pipe for many kilometers, causing joints to move and exerting fatigue, shortening its lifespan. If anyone can recall, there is an incident in Sungai Selangor one time ago that due to this water hammer, the pipe was burst and the large diameter of pipes fly as high as 2-3 story high, you know. And we are lucky that nobody died. And that is the incident of the impact or the pressure transient that can cause by the operational activities, such as pumping, valve operation, and can only be identified by very high resolution monitoring, 100 of pressure readings per second. It's high-tech monitoring. The other portion is pipe leaks. These are quite common. These are precursors to catastrophic failures, because pipes usually leak before they burst, and that is the symptoms that we can look at. So if a pipe leak can be identified before the pipe wall fails, it means that a proactive repair can be carried out rather than a reactive repair, which will usually require the main to be shut down, may involve mobilizing a team during the night and results in a higher repair cost. So if a pipe does burst, it may generate a pressure transient, which can travel long distances along a pipe. So the use of high resolution pressure monitoring can detect this pipe burst in real time, meaning that response crews can be mobilized immediately to effect the repair, which reduces the risk of life and property from a catastrophic mains failure, and also minimizes the loss of water, thus helping to reduce the non-revenue water. Anyway, I don't intend to touch more on this topic and will leave more time to the two esteemed speakers to elaborate further on how this trunk mains monitoring works, and MWA hopes and look forward at the root cause of the transient events on trunk mains which had a history of bursts, and we hope this would mitigate the cost and therefore better optimize the network. So we hope the participants can put up your question and your queries, and this is an opportunity to ask from the two experts on this monitoring works. So finally, I take this opportunity to thank Xylem Incorporation Malaysia and institutional members of MWA for coming forward to share their experience to service providers to innovate and to provide more customer focused and resilient services for the betterment of our industry. Also, a big thank to Proten Group for hosting this webinar. So may we have a very good seminar this afternoon. Thank you. I pass back to Dennis.
Okay, so I think it's time for me to step in here. Thank you very much, Datuk, for your insights. Very wise words there. I'd also like to thank ProTemp, Denise and her team, and also MWA for hosting this event, for inviting us to participate. We're very pleased to be here and share the experience that we've gained over the last number of years. We've been working in Singapore, but also the last couple of years in Malaysia. We can share our experience with you. And as Datuk said, please don't hesitate to ask questions. Myself and Matthew would be more than happy to answer them at the end of the session. So to introduce myself, my name is Martin Shaw. I'm a non-revenue water solution architect for Xylem. I'm based in Shah and my role is to visit water companies throughout Southeast Asia, talk to them, learn from them, and discuss their non-revenue water problems and offer them solutions that Xylem can help with from our advanced portfolio of our technology solutions. One of the companies that we have been working with is Selangor. Obviously, they're a large company and they have taken a very proactive approach to non-revenue water management over the years. They've got something like 2,000 DMAs, which means that their distribution network is well under control. But they have always been aware that their trunk mains haven't been monitored as much as the distribution system. And even though they have been undertaking leakage surveys on their big pipes for a large number of years, they understood that the leakage surveys were finding a large number of leaks. But because of the length of the network, it means that you can only undertake surveys once every couple of years. And that means that the runtime of your leak could be months or even years. So you're letting water run away. So you're losing water, but it's continually damaging the pipe. And as Datuk said, many bursts start off as leaks, which get bigger and bigger. So at the end of 2017, Selangor decided that they wanted to undertake some more advanced monitoring of their network. They issued a public tender to monitor 6,000 kilometers of their trunk main. But Xylem won the contract, and we're now roughly 3/4 of the way into a 3.5-year term. So this webinar is going to have a look at how advanced technology has been used to monitor the Selangor trunk main system, and it helps them keep control of their large assets. So I'm going to introduce you now to Matthew Kennedy. He's the project manager. He's also based in Xylem. And the Selangor project is just one of a large number of projects that Matthew's currently overseeing. So he's the best person to take us through. So I'll hand you over to Matthew, and then we'll answer questions at the end. So Matt, all yours.
All right. Good afternoon, everyone. Thank you very much, Martin, for the introduction, and thank you, Datuk, also. Denise, I believe I need to have permission to share my screen so I can share the slides. Thank you. Okay, so hopefully everyone can see the slides I have presented currently. First point to note, I'm very sorry I don't look like my picture. 2 months of MCO has meant my hair is considerably longer than what you see here. What I would like to present to you this afternoon is something that has been taking up a great deal of my time and my interest for the past couple of years, as Martin has alluded to. So what I would hope to go through this afternoon would help you learn about the solution that we have provided to Selangor, a few details about their trunk main network, and how they have successfully implemented this system in partnership with us. A little bit about the current progress of the project, and some of the lessons learned that we've had so far since we are partway through. So to initially take you through the solutions that we are providing here, Xylem provides a number of network analytics solutions for this particular case, or relevant here. These cover 3 key products that we call View, LeakView, and SurgeView. And the purpose of these products is to assist with decision support, NRW reporting, 24/7 leak monitoring and alerts, and asset failure prediction through the monitoring of damaging surges within the pipes. So these products are also supported by our own hardware, which you can see here. This constitutes of a remote terminal unit and a pressure sensor and acoustic sensor. The RTU itself can also be used with flow meters and other types of sensors, and can be powered with a number of different power sources. But the key part here is the pressure sensor, which is capable of recording up to 256 readings per second. This facilitates the transient monitoring that I've just mentioned. And the hydrophone also forms a key part of the solution here. So you can see this perhaps on the next slide. The hydrophones and the pressure sensors both form a key part of the solution. So when a burst occurs on a pipe, it can initiate very suddenly, resulting in a drop in pressure, which we refer to as a transient. This sudden drop in pressure can travel along the pipeline at high speed and for long distances, but can only be picked up with very high resolution recording of pressure. Typical pressure monitoring devices wouldn't detect this type of signal. So for this reason, we use the pressure sensors. However, not all leaks occur as bursts. They may start small and grow over time. And these types of leaks might be recordable using hydrophones, which require closer spacing. So by using
Matthew, sorry, Matthew, I need to interrupt you. I think we cannot hear you very well.
Okay.
You seem to be breaking up. I'm not sure if it's your internet connection or your speakers, or try again.
Just give me one minute.
Yeah.
Okay. Can you hear me now?
Yes, much better. Thank you.
Okay, please step in if I'm mumbling. Okay, so to recap, we use those 2 different types of sensors, the pressure sensors and the hydrophones, to detect leaks in the different manners that they may occur on the pipes. So this type of solution, which we call LeakView, can be deployed anywhere across your network. For this particular project, we're talking about the trunk main transmission system, the larger pipes that you can see on the right side of this diagram, but it's entirely possible to have this deployed within your DMAs as well, although that hasn't formed part of this project. The SurgeView solution that we're talking about monitors the pressure transients that I referred to on the network. So frequent occurrences of these pressure transients or excessive magnitudes of transient can introduce fatigue to your pipes, which over time may reduce the asset lifetime. It's important to identify these early on so that you can address the operational factors that may be causing them and increase the lifetime of your assets. Both of these solutions are supported through our data analytics platform, View, which integrates data from multiple sensors or other platforms and runs network analytics on those data feeds. All of this can be presented through a system of flexible dashboards and reports to help you understand your data better and deal with the deluge of information that's coming in. So a very quick screenshot of what that system looks like without taking you through a whole setup of the system. You can see there the data plot and some of the sensors that you might expect to see on a map. So now I'll take you through a little bit on the Selangor. Now, with you all being from Malaysia, I would expect you know where Selangor is, so I won't spend too long on this. But in terms of as a utility and their network, they're dealing with around 2.4 million customer accounts covering approximately 11 million people, the majority of that being domestic supply. Now, from our point of interest, that's 28 or 29,000 kilometers of pipe, of which 6,200 kilometers are trunk mains, greater than 300 millimeters in diameter. The majority of those, 80% being mild steel in construction, although there is a mixture of other materials, including ductile iron and asbestos cement across that part of the network. Selangor have had a stated aim to reduce their high rate of non-revenue water. In January 2018, this stood at 31%, and I know they've had some success in reducing that in recent years. And that's been made up of quite a number of leaks and bursts every day. The goal has always been to reduce the runtime of these leaks and bursts and therefore reduce the volume of water lost and to be able to pinpoint the location of these pipe failures. Similarly, from a proactive perspective, it's important to them to identify the causes of these pressure surges and mitigate them before they cause the pipes to burst. So Selangor managed this with this three-pronged approach. They have a passive network, a call center to pick up customer notifications or leak notifications across the state. And that would be the passive approach. But they do have a proactive approach of line sweeping with technologies such as ground microphones, listening sticks, and acoustic correlators. So supplementing this is the Xylem system, which provides both a proactive and a reactive solution to be able to detect leaks before they occur and react to them as quickly as possible when they are detected. So why trunk mains in particular? Active leak management can prevent costly shutdowns of the network. And since trunk mains convey a lot of water, it's important to keep them running all the time to avoid shutdowns to large numbers of customers. They are the backbone of the network. In particular, in Malaysia, these trunk mains can be in remote and frequently visited areas. So often you may rely on the public to inform you of leaks. Not really possible when these are in plantations or in the jungle. Not every leak is like the one you can see in the picture here, which could be seen from a long way off. Quite often they're hidden underground and very rarely visible. The large pipes that you can see in the picture here, they're not always suitable for leak sounding with the equipment such as correlators and microphones. They're hard to access, and when they do burst, you can have very high leak rates. Similarly, from the proactive perspective, they are also subject to large operational pressure transients, as they're usually part of the pumping network that you all have. So just to check that you're paying attention, and before I waffle on for too much longer, I'll stop there temporarily whilst Denise introduces the poll that we mentioned.
Yeah, Henny, you can pull up the poll. Okay, participants, these are 3 short questions. We would like you to answer them, and we will display the results immediately after. Matthew, you can check your sound, because I think just now your sound was also breaking up a bit.
Okay. Okay, we okay to continue?
Is Henny? Do we have the results now? Okay. So do you monitor your trunk mains for leaks? We have 69% yes and 31% no. Do you know if there are any pressure transients in your trunk mains caused by pumping or buff operation? 55% yes and 45% no. Do you think that the trunk mains are being monitored sufficiently in Malaysia? 34% yes and 66% no. Okay. So here's our answer. So I will close that. Yeah. So Matthew, you can continue. Thank you, everyone. Don't forget to post your questions for our speakers. Just click at the Q&A icon at the bottom of the screen. Matthew, over to you.
Okay, thank you very much. So now I'll take some time to describe how we have implemented the solution specifically within Malaysia, or within Selangor. I mentioned the 6,000 kilometers of trunk main. So we're covering that with around 1,800 sensors, with both pressure and acoustic monitoring. These are all powered with solar power to reduce the amount of maintenance. As I mentioned, they're in quite remote areas, so it's not like we can just open the front door and go visit them. We're providing both the LeakView and SurgeView solutions that I mentioned earlier on. And it's important to state that the delivery of this project is a collaboration between Xylem and Selangor. None of this would happen without Selangor's help in terms of the deployment and maintenance of the sensors, the survey and the planning. We assist with the design of the solution, the supply of the equipment, and we monitor the system for alerts and issue those to Selangor when we notice anomalies on the network so that they can tackle those as leaks. So we have several types of deployment that enable us to speed up the deployment of the equipment in the field. They're all solar powered. You can see here in the pictures that we have a typical deployment that is fitted to a steel pole, and another type that is welded to the trunk mains in the lower left-hand image here. All of this is powered with a rechargeable battery on the inside of the enclosure there. And we refer to these as both the pole-mounted and bracket-mounted types of deployment. This enables us to go into both chambers and on the S-bends that are typical within Malaysia. So at this time, current status of the project, even with the MCO slowing things down, we're at around 1,300 sensors currently deployed, and with around 80 of these going in every month. That's covering approximately 250 pipelines across the state and enables us to detect around 4 leaks per week. Some weeks we have 7, which is a leak a day. Some weeks we have a little less. And as we install more sensors, this is steadily going up. So a year ago, when we had less sensors installed, we were detecting around 1 leak per week. Now, what that means is those 1,000 sensors have now accumulated 500,000 days of operation. And that generates a lot of data. I mentioned the 256 pressure readings per second. Well, that's 2.5 trillion pressure readings, 7 million acoustic recordings. This is way more data than a human being could ever hope to look at, let alone comprehend what this looks like on a piece of paper. So this is the benefit of the real-time detection algorithms that we have, which have enabled us to identify 170 leaks in 2019. All of these have been fixed and repairs. It's a key benefit to Selangor's leak reduction strategy. We also do pick up quite a lot of interesting stuff on the acoustic recordings. It's not just leaks we hear, cars going by, animals, the occasional argument. There is a varied soundscape out there in Selangor that the acoustic sensors are capable of picking up. But all of this is monitored, transmitted, recorded and analyzed in real time, 24/7. So if anything happens at night, we know it's happening even if people are sleeping. So the successes of this type of deployment, we've managed to have a standard design that I mentioned that applies to most of the varied situations across Selangor. This has enabled the rapid deployment so that we can go from 0 to several thousand sensors relatively quickly. We've managed to locally source a good portion of that equipment, which helps speeds up the deployment. And some other key benefits in terms of the monitoring of the system. The response times that we have are often before the public are aware of a leak. So if a burst is occurring, we have many cases where the alert that our system is generating is before the public are aware that the pipe has burst. So it's reducing the runtime of those leaks. With the hydrophones, we're able to pick up the smaller leaks before they burst, which again reduces the runtime of them from weeks or months down to days. And should those leaks reoccur, if you have a particularly degraded section of pipe with leaks occurring one on one day, another the next week, even after the first leak is repaired, the system is there to pick up the second or third or fourth leaks. So it's really good for picking up leakage and keeping it down. We also have a good awareness of the leaks that are occurring beyond the project pipelines that were installed upon. So even though we're on the trunk mains, some of the connected areas we're capable of picking up leaks in. Now, any project wouldn't also be without its challenges. Malaysia does introduce some of its unique challenges, which I'll get onto down the bottom. But one of the key points that I've alluded to is the coordination required for this quantity of sensors and the quantity of data that's coming in. This leads to communication challenges that need to be overcome. As a utility, Selangor will have gone from no leak alerts to hundreds of alerts just because of the network that has been installed. And finding a way to ensure that the leak detection teams can address those is very important to get over when running a project like this. It's also a new technology, so education and appreciation of how the system works is key at the beginning of any project like this. Training is required to bring staff up to an understanding of what the sensors can do and the benefits and constraints of the system. Now, from a Malaysian perspective, we have faced a few issues with the sensors themselves, both in terms of theft. You can see there that everything but the kitchen sink has disappeared out of that enclosure. And also the wildlife has provided some rather unique challenges. Rats, snakes, and with the picture in the middle, we do have the occasional monkey that likes to pull on the sensor cables and damage them. We don't tend to suffer these types of problems in Europe, for example, there not being any monkeys there. So what have we learned from all of this data that's coming in and the monitoring networks that we've installed? The pressure transients, an example of which that you can see at the top right here, these can travel a long way, up to 30 kilometers, and they may be present before a leak fully surfaces. It may not be visible above ground, but the burst transient may have occurred on the network before the leak surfaces. So you do get a good bit of lead time even with the bursts. by using this type of system. We've also found with the acoustics that typically with hydrophones, the expectation is that they can pick up leaks within a distance of around 500 meters. What we find with this type of system is that leaks of certain sizes can generate additional flow on the pipeline. And the sound of this flow in the pipeline through fittings can be picked up at a much larger distance. So I'll show you an example of this a little later on. And another important point about this system is that not every leak produces a pressure transient. Not every leak produces a clear acoustic signal. So it's important that we use multiple parameters to maximize our chance of detecting leaks on the network. So just pressure sensors or just acoustic sensors will only pick up a certain subset of what is occurring. We've also found that the behavior of pumps, their on and off timings, can be indicative of when leaks are occurring on some of the mains. And in a similar vein, we've found that the trigger levels for altitude valves and pumps are important for controlling the transients on the network. So I'll take you through some specific cases we have for some of this. This example here was a particularly large leak that was detected. And if we were monitoring the network with a standard set of pressure loggers or at our balancing tanks, we might have some alerts set up so that when the level in the balancing tank goes below a certain threshold, we may trigger an alert for a low pressure. Now, on the center graph that you see here, the green line is pressure. That type of alert at the balancing tank may only get triggered somewhere within the red circle after pressure has dropped out of its typical daily range. By using the transient sensors, what we've been able to do is identify the presence of this leak a full 6 to 12 hours before that type of monitoring would have picked it up. So 6 to 12 hours ahead of what you would see using monitoring of your balancing tanks. So in the graph at the bottom, we can see the high resolution pressure data. There is a 6-meter, very sudden drop in pressure at 10:45, the night before the leak was found. And then a few hours after this, another 11-meter drop in pressure at 3 a.m. in the morning. On the middle graph, you might also be able to see some light blue lines. This is measuring the acoustic energy that's inside the pipe. And we can see that within the red circle, there is an increase in the acoustic energy as the pressure is dropping due to the sound of the leak. So both sensors were able to pick up this particular leak. And we can see in the picture on the right-hand side, it was a very large one. And by identifying this before typical monitoring would, we were able to reduce the runtime. The public did not call this one in. So here's another example. This case study shows being able to detect leaks that may not have surfaced from a greater distance than we typically have with acoustic sensors. So in this particular case, we had a 900mm mild steel pipe, and the leak occurred 1.5 kilometers from our sensor. It was a very large leak, 20 liters per second. You can see in the picture here. But this is only after excavation. The leak itself was flowing directly into a nearby drain. It was not visible from the roadside, and it was not in an area where people would call this in. On the graph below, you can see the green lines, which are showing the acoustic energy being recorded. These suddenly increased around the 28th of April. And that increase in energy was indicative of the leak. Following the repairs, that energy dropped back down again. So it was important using this sensor to be able to pick it up at both an unusually large distance and with a buried leak that did not surface. This is because we were able to pick up the sound of the flow within the pipe as a result of the leak. A third case study I've got here, I referenced how pumps may be indicative of leaks on the network. In this particular case, we can see the red line on the chart. There's a daily pumping pattern that's going on. Towards the right-hand side of the chart, we can see that the line gets blurry. The pumps are turning on and off more and more frequently. This is because they're trying to pump more water as a result of extra demand caused by a leak. We can see on the far right-hand side of the graph that after the leak was repaired, the pump frequency returned back to normal. So this is an indication of pumps showing the presence of a leak. But one of the key aspects of the system is using the high rate pressure, the pressure transient data, to determine if the pumps or other network assets may be damaging the pipelines before the leaks occur. So using this method, we've identified over 20 operational issues across the network. They're relating to pumps, valves, or unusual demand patterns. Now, the benefit of this is if we compare to traditional pressure monitoring sensors, we can see on the three charts on this slide that traditional pressure monitoring may be recording at, say, 15-minute or maybe 30-second intervals. By doing so, we don't pick up the true peak or the true trough or low pressure that may be occurring. Using the high resolution pressure, we can identify excessive energy that's being introduced to the pipes. So with the graph at the bottom, we can see that there is a pressure spike here that goes up to 135 meters of pressure. But on the central graph and on the top graph, at 15-minute recording intervals, the pressure is only increased to half of that, 70 meters. So it wouldn't appear to be an issue unless you were using the high resolution pressure sensors. So here are some examples of some of those issues that we pick up using this method. We may have overactive pumps where they are triggering too frequently, on and off every few minutes. This might also apply to valves, altitude valves on the network, where these can be fluctuating every few seconds, open and shut, open and shut. This introduces a cyclic loading to your pipes, which may introduce damage. In the middle graph, you can see an example of an unnecessary surge. So the peak pressure of 135 meters is some 70 meters more than the final pressure achieved after the pump asset has been turned on. So the pump doesn't need to introduce 135 meters of pressure, but that has happened. And if we find a way of reducing the spin-up speed of the pump or mitigating that pressure transient, then we can achieve the end pressure of 70 meters without damaging the pipes. The bottom graph, we can see an example of potential cavitation on the network. So when we're opening and closing valves, turning pumps on and off, we may get some very short periods of zero or below zero pressure, which is particularly damaging to pipes. We wouldn't pick this up with the low rate pressure sensors, the 5 or 15-minute readings of pressure. So the zero pressures are also being picked up by our system. So that's been a quick run through of some of the issues that we've faced on the network and how we've implemented the solution for our Selangor. So some take-home messages from that in terms of conclusions. We've been able to show that we can provide an early warning and reduce leak runtime. We can identify recurring leaks, so we can identify the source of NRW and keep it down. We can use multiple sensor feeds to identify the leaks rather than just one or two, acoustic or pressure. And we're able to identify the causes of leakage to prevent further loss. So this is a very active method of leak detection. The system we're using effectively complements the existing leak detection methods that Selangor have. So we're able to trigger further surveys in the field if there is a particularly difficult leak to find. And so in sum, we've been successful in setting up the monitoring system on Selangor's trunk mains. We're looking forward to continuing to install and monitoring on them over the coming years. And now I would like to open the floor for any questions that you may have for me and Martin. So thank you very much for listening.
Thank you, Matthew. Thank you, Martin. You can see the Q&A at the bottom of the screen, so you can just click on that and view the questions and answer them. Can you see the questions?
Yes. Okay. So I've just loaded up the questions. The first one is too much echo on speaker. So I'm very sorry. I do apologize. This isn't normally a problem for me. The second question, which is technically related, what are the selection criteria to put the pressure sensor and hydrophones in the network? So this will depend a lot on your needs as a customer. What size of pipes you have, what materials you have, and the pressures you have within those pipes. It's a very difficult question to answer in general terms, but we would require technical information on your pipe network to provide the best solution in terms of the spacing or of your pressure sensors and hydrophones. Martin, is there anything to add on that one?
No, I'm happy with you answering that one.
Sure. Okay, I shall move on to the next question on the list. I have 12 to get through here, it seems. Have you ever done any survey on the leaking compared between developed and developing countries' cities? How much is the economics impact? This would be significant to those cities. So we at Xylem, we do have this solution running around the world. We do have customers in Malaysia, in Europe, the US, Australia, and New Zealand. And so I can feedback perhaps some of my personal experiences between some of those different projects. So leaks occur regardless of developing and developed countries. The economic impact will vary depending upon the labor it was required to repair those leaks. So somewhere like Malaysia, you may be more inclined to search for the leaks with a team, whereas somewhere in Europe, you may need further information on the location of the leak before triggering your leak finding teams. Martin, is there any further points to add on this one?
The only thing that I would say is I would think about the inline tools that we have, the Smart Ball and Sahara. You know, they're picking up leaks around about 3 kilometers on average. And I don't believe that changes from whether the country is considered developed or non-developed. I think the number of leaks are pretty much the same. So my answer to that would be, I don't think it changes from developed to non-developed.
Okay, thanks, Martin. So I'll move on to the next question. What is the average interval of the sensor installation along the trunk mains? How do you prioritize the installation? So this is related to the first question I answered. The spacing between the sensors and the interval of the sensors does depend upon your requirements as a customer. Do you want to focus on the awareness of the leaks? Do you want to focus on the detection of bursts? Or do you want to focus on the pinpointing of those leaks? So it's a discussion that we would have when we are designing the solution. For this particular project, you will have noticed that we have 1,800 sensors that I mentioned and 6,000 kilometers of pipeline. So the spacing is in the kilometers between those sensors. So referring to the next question in terms of the objective of the project, is it to detect leaks or to detect the volume of those leaks? So this is twofold. Our Selangor's concerns were to identify bursts and to reduce the runtimes of those bursts and the causes of them on the network. So detecting them is an objective, but to reduce and mitigate the causes of those leaks is an upstream objective of that. And by doing so, we can reduce the volume. So reducing the volume of the leaks is not a specific objective of the project, but it is an end result of what we are doing. Okay. So moving down to the next question. How Xylem have solved or prevented the theft problem that we have been facing in Malaysia. So yes, this isn't something that we as Xylem have solved. We, between us and Selangor, have implemented a solution that has been successful in reducing the amount of theft that we're seeing. We do see a lot of people interested in the equipment, but as a result of introducing anti-theft measures on our enclosures, we've seen a reduction in that, and it doesn't cause a significant issue to us currently. Okay. Moving further down the list of questions. So the next question would be how to use pressure sensors to find out leaks or combined with acoustic sensors. So for this, I would refer back to one of my earlier slides. The pressure sensors are capable of detecting pressure transients on the network. These occur when there is a sudden drop in pressure as a result of a burst. The acoustic sensors are capable of detecting small growing leaks on the network, and they can detect them at shorter distances. So the pressure sensors can detect at a longer distance, but they detect the bursts as they occur. The hydrophones will detect at a shorter distance and will detect the leaks as they grow. We use the combination of those to detect these two different types of leak occurrence. Okay. Next question. Martin, I'll let you answer this one.
Yeah, sure. Okay. Yeah, so the two techniques are really complementary when we're talking about smart ball and when we're talking about permanent acoustic monitoring, because as Matthew's just said, the permanent acoustic monitoring will only detect acoustic energy from the leaks within range. So it may be a few hundred meters, or as Matthew has said, in some cases it can be a kilometer or more, but that's unusual. So we do have to acknowledge that for the acoustic sensors, they're only going to pick up the leaks that are closer to the sensors. Matthew has spoken about the sensor spacing. To detect bursts, you can have them many kilometers apart. But to detect acoustics, you need to have them closer together. And so this is really where the smart ball comes in, because the smart ball is designed to be installed in a pipe, and then it's a free swimming device. You let it go and it can travel many kilometers along the main, and then you catch it at the other end. And so what that does is it surveys long sections of pipe in one sweep. And because the ball passes directly past the location of the leak, it means it can detect leaks that are very, very small. So in terms of which technology is better, I think each one has their place. They're both complementary. So they've both got pros, they've both got cons. But yeah, I would say that using them together would be the ideal solution. And the next question. PVC pipe trunk main with low pressure. If we're talking about leakage, I would again refer to Smart Ball or Sahara, because they will pick up leaks at low pressures. I think 10 meters is just about the lowest they would go to. But again, because the sensor travels to the leak and you're not looking for the acoustic energy of the leak to travel to the sensor, it means that your inline leak detection tools will pick up leaks that are very, very small. how to determine trunk mains to be replaced or repaired. If we're talking about steel, we do have technology that can calculate the remaining useful life of a pipe. So what you would generally do is you want to know the thickness, you want to know the wall thickness of the pipe, because it's a lot cheaper to undertake analysis and undertake pipe condition assessment than it is to just go and replace the whole pipe. You might be able to replace one or two sections. I mean, I think the US Environment Protection Agency are finding that something like 70% of pipes that are replaced still had remaining useful life and could be left in the ground. So certainly most, as we've heard, most of the trunk mains are metallic, and you would pass, if it was me, you would pass electromagnetic condition assessment tool. You can use free swimming devices as well, which can also do long sections of main in one run, and they'll follow the flow of the pipe, and they'll tell you the pipe wall thickness, where you have internal corrosion, where you have external corrosion, and then you can concentrate on those sections of pipe to determine whether you can repair them or whether they need to be replaced. To distinguish broken PVC pipe caused by water hammer, I would say the best way to do that is to install very high resolution pressure sensors. Because Matthew said previously, unless you have very high resolution sensors recording at many hundreds of readings a second, you're not going to know that that your pressure transient exists. So the first step I would make is to install the transient monitors around the network and see if you do have problem or if you don't. And is the hydrophone installed permanently on this project? Yes, it is. That's the advantage. The advantage of having a hydrophone installed permanently means that within the range of the acoustic energy that travels from the leak, it means that you will detect the leaks as they break out. And that's important to firstly reduce your NRW, because as many people I'm sure are aware, there is awareness, location, repair. The faster you are aware, the faster you locate, the faster you repair, the less water you lose as NRW. So in terms of installing the hydrophone permanently, then that's the big advantage that you get from that. Big leaks lead to long downtime. Any way to overcome in future trunk main design installation? Well, one thing that Dato mentioned earlier, he spoke about the material, he spoke about the quality of the workmanship, and we should also remember that there is hydrostatic testing, which should also happen. So when you bring a new pipe into commission, it should be hydrostatically tested to make sure that the construction is sound. So in terms of design, I don't know if the design can change. I think Malaysian engineering is very sound. You just have to look at the city centre to see the construction that we have here. I think the design is fine, but as Datuk mentioned, maybe the installation could be looked at in some cases. Does the system work with non-metallic pipe? Yes, it does. There are implications because, as many people will know, metallic pipe allows the energy from the leak to travel better than the plastic pipe. And as we've mentioned before, most of the trunk mains are metallic. So although the system does work with non-metallic pipe, you would usually expect that if the distance of the leak noise doesn't travel so far, you would expect that you would have to put your sensors closer together if you wanted the same sort of coverage. Is there any term and condition in trunk main to make sure the sensor equipment are running well? Okay, Matthew, I think this one can be handed back to you. How do we know that the equipment's running well?
How do we tell the equipment is running well? So number one, it must be transmitting data. So online, offline is the most obvious example. However, we can tell if the sensors are faulty or if they have been stolen, if they have been chewed through by rats. This produces a very distinct signal. So in the same way that we're able to notify of leaks, we can also notify of rats, or a high confidence of something like a rat chewing through a cable, or somebody grass cutting through a cable, or something similar like that. So we do have continuous monitoring of the condition of the sensors as well. So next question, what are the definitions here for leak and burst, such as by volume, pressure, response time, etc.? This is a really good question. There isn't a clear definition between both leak and burst. This can vary depending on who you talk to. However, qualitatively, we would consider a burst to be something that occurs suddenly and with a large volume and noticeable transient onto the network. A leak would be something that starts small and continues to grow. Those can occur with a range of volumes and pressures. Martin, is there anything that you would like to add on that definition?
The definition I tend to use is a burst needs a repair immediately and a leak doesn't. Very, very loose, very general, but that's how I tend to think about it.
Okay. So next question, what are the recommendations on where to install transient monitoring equipment? So if you have pumping assets on your network, it's good to monitor these and assess how those transients may be generated by your pumping assets. That would be one example. Critical infrastructure that is at risk of failure, where the impact of the failure of that infrastructure may be excessive. And in particular areas where you may have a leakage problem. Third question here, how NRW changes after deployment of 1,300 acoustic sensors. So this isn't something that we have a detailed figure on. Selangor have published their latest NRW figures. So as a result of their strategy over the past few years, they have been able to reduce NRW. Our system is part of that, but it is not the only thing that they are doing. So that's the best answer I can give you at the moment for that particular question. What is the minimum pressure for the system to work? So the system can work at a range of pressures. Lower pressures in the network will decrease the magnitude of transients that we see, and they will normally decrease the distance that you would expect to hear acoustic signals in the pipe. So at lower pressures, we might expect that the distance for signals to travel to be shorter. That said, we do have examples of leaks being detected at very low pressures, 10 meters or so. So the system is capable of working at low pressures, but it may be more effective with higher pressures. So next question. So I have mentioned that it can pick up the potential leak location, pinpointing. The system is capable of doing this. With the design of the system that we have for Selangor, normally exact pinpointing of a leak location is possible with acoustic methods when the sensors are spaced close together using acoustic correlation. So it's the same method that would be used when you sweep the lines with acoustic correlators. The way we have the system here is the sensors are placed further apart. So exact pinpointing of the leak locations is not normal, although it is possible in some cases depending on specific sensor spacings. Can it predict the volume of leakage? In short, no. I don't think so off the top of my head. When we detect a leak, the size of the transient that we observe or the strength of the acoustic signal is it's a function of not just the size of the leak, but also the pressure within the pipe, the size of the pipe, the flow rates within the pipe, and a number of other ground condition or other factors. So just using the data that we're monitoring, we can't predict the volume of the leakage, but we can get a ballpark idea of it's a big one or it's a small one. Another question here, can we pinpoint the leakage location? So I've answered similarly just a moment ago. But just to add to that, we can show the location of that. If the sensors are close enough together, we can show the location, the expected location of the leak on a plot when the data is sufficient. Right, we have another question here on budgetary cost for 100 kilometers. I might suggest on this one, if you have a specific case that you would like to look at, that you get in touch with us and we can provide a suitable solution. There are too many variables to say exactly for 100 kilometers of mild steel, it will be this much. So do get in touch if you have something you'd like us to look at.
Yeah, I think one factor is the number of sensors, but then we also have to look at whether you purchase the sensors or rent the sensors, and we also consider whether we do the analysis or you do the analysis and the alarm. So as Matthew says, there's a lot of different factors that come into play. So please reach out to us after the presentation, and we can help you with some idea of a budgetary cost.
Okay. Next question. Is the sensor installed permanently or moved? So for this project and for many of our projects, we work with permanently installed sensors. This is how we're able to monitor 24/7. For perhaps some smaller cases, we do offer some more flexible arrangements in terms of moving sensors, but it will depend on the problem that we're trying to solve or detect. Okay. Martin, would you like to answer this question? I think you've got greater experience than me.
Yeah, okay. Most severe experience when starting the work process to decrease the level of water loss. To me, this sounds like more of a general question, and I'm sure that there's a lot of people listening here in Malaysia that understand how to develop non-revenue water projects, how to plan a strategy. So if we're talking about severe reductions in water loss, I would start off with running a water balance. Go back to basics, run a water balance, calculate where most of your losses are, whether they're real losses or apparent losses. And with the real losses, if you can break it down further into losses on the distribution system or losses on the trunk main, and your water balance really is the basis that you can use to plan your work forward, to help you identify where the most losses are. Because if you can identify where most of the losses are, that's where you're going to get your biggest bang for your buck. So I'm not sure if that answers the question, but that would be my suggestion for that. Okay. Volume of data that you collect.
in short, terabytes would be the volume of data that we collect. It's a lot, of course, with thousands of sensors. The quantity of data will vary depending on how many sensors you are using. How long do we store them? So that's going to depend on your needs. We can be flexible with the length of time that the data is stored for. A lot of the lower frequency data, say every 30 seconds or every few minutes, is stored for a year or more. I just want to check at this point because I can see more questions being added. Denise, do we have a time limit on when the Q&A is finishing? I don't want us to ramble on for too long.
Let's see how many questions. We don't really have a time limit, Matt,
Okay.
so you can try and answer all of them.
Perfect.
Okay, I think if by 4:30 we cannot answer all questions, then we may have to answer them via email.
No problem. Okay, we shall continue on.
Yeah.
So next question. Can your system be used on non-metallic trunk mains? I think we've answered this question previously. How about noise correlators and leak correlator methods? So I can say for Selangor's case, yes, they are using them as part of their NRW strategy. Our system and those methods complement each other, and that is part of the success that they've had. Martin, would you like to add anything on using correlators at all?
Yeah, as you say, it's complementary, really. I would also throw SmartBall into the mix because the issue that you have with leak noise correlators, particularly on big mains, is that we know that due to the surface area of the pipe, leak noise does attenuate very quickly, which means that if you get a small leak, the energy will not travel the couple of 100 meters that you need to get onto the fixtures and fittings that you have on trunk mains. You know, they're usually a couple of 100 meters apart. So that's the disadvantage of the leak noise correlators, whereas the SmartBall, because it goes past the leak, it will detect it. But in terms of the methods being complementary, you have real-time monitoring, so you know as soon as something happens, and then you also can use different techniques to actively go out and try and find the smaller leaks that won't be detected by the permanent installations because they are a number of kilometers apart, and the leak noise certainly won't travel that far on the big pipes. Will monitoring trunk mains significantly reduce the leaks in the state, considering trunk mains are steel? If so, what is the target? Answer the second part first. What is the target from trunk main reduction? In order to calculate what the target is, you have to calculate what the losses are. And the only way you're going to know that is by, to me, if you can run a water balance. So you know you have a water meter at the balancing tank, you have a water meter at the service tank at the other end. If you can measure what your losses are, and you can do that on a sample of pipes, it will give you an idea of what your losses are on the trunk main system. That would be the way that you can set a target. One way that you can set a target. The other way is to look at how many leaks you're finding and to make some sort of assessment of what the flow rate is when you go and fix the leaks. Will monitoring the trunk mains significantly reduce the leaks in the state, considering they're steel? Well, we've seen from Selangor that most of the pipes are steel, but we're still getting 4 leaks a week. So even though the pipes are steel, we're still getting a reasonable amount of leakage on them. Will it significantly reduce the leaks? It depends on what the condition of the pipe is. If you've got a lot of leaks, yes, it will. It will significantly reduce the leakage. If you don't have a lot of leaks, no, it won't. But you add another factor in here, and that is, if you remember at the beginning of the presentation, Matthew showed some enormous bursts. And I've seen videos of huge bursts. And that is where you get a significant saving. So if you can find a leak and you can fix a leak before that pipe fails and before that enormous amount of water is lost, that's where you're going to make a real saving. So yeah, that's another area where you can make big savings in NRW by actually preventing bursts before they happen. Key to your success in controlling NRW in trunk main pipeline, if the asset condition is not ideal, pipe condition assessment, that's what I would suggest for that. Use technology that will tell you what condition your pipe is in. It will tell you if you have leaks, if you don't have leaks. And technology can also be used to tell you if you have corrosion coming from the outside or the inside out. It will also help you identify whether the whole pipe is bad and needs replacement, or only whether individual sections are bad and need replacement. So there are tools, there are technology that are available to help you control your NRW in the trunk main pipeline. So I would suggest undertaking some condition assessment work to work out exactly what condition the pipe is in. Financial perspective, solution more economical than traditional method before implementation. We've got some data on this, haven't we, Matt? Are you familiar with the costs when we compare it with correlators?
Off the top of my head, no.
Okay. Yeah, this is a tricky one to answer. Yeah, I think a lot of it depends on the condition of the pipe and how many leaks you're getting. If you're getting a lot of leaks, again, the problem with the correlator method is that because the leak noise only travels a certain distances, it will miss leaks, the smaller leaks that are in the middle. And the other disadvantage of the leak noise correlator survey is that you run a survey today, and then you might get a leak tomorrow. And that leak will run either until your next scheduled survey, which might be 1 year away, or it might be 3 years away. And your leakage runtime is usually considered to be half the time between surveys. So if you have a big trunk main network and if you survey your mains using a correlator every 3 years, then your average leak runtime is 18 months. So that's the problem with that. So it will run for 18 months or until the pipe fails. And then, as we've seen before, when the pipe fails, that's when you have a lot of water that's being lost, and it can also damage property. And as Datuk mentioned earlier, there's danger to life as well if you have catastrophic failures. How regular is service required? Matt, can you take that?
Sure. So the equipment that we're using is fairly low maintenance. I mentioned that we have a solar system that continues to power through a battery so that we don't face any power problems. However, that doesn't mean that there's no maintenance or servicing required at all. We do face the theft and damage issues that do require visits to the sensor sites to bring them back online. So those fairly random events can occur on a project like this, enough to keep people busy every now and again visiting sites out in the field. For example, we had someone crash their car into one of the sensor points. It's not something that you can predict happening. From a typical maintenance perspective, there's very little that needs to be done with the hydrophones and the pressure sensors on a regular basis. They will continue working as expected for several years. Under normal circumstances, no rats, monkeys, vandalism, lightning strikes, car crashes. What is the average lifespan of the equipment? So this will depend a lot on the conditions that we put them in. But we will be looking at several years for this to run to completion. The project that we're running at the moment All the sensors that were installed 2 years ago are still in operation, and we would expect those to be still running in 2 years' time. And this relates back to the previous servicing question. We're not having to go out and service the particular sensors to keep them working unless we see that a problem has occurred. Other than Selangor, have any other places, where else have we installed this type of system? Lots, all over the world. I can think of projects that we are running across China, India, Australia, the Middle East, Europe, the US. I could go on, but we have most of the world covered, especially in terms of time zones, and several, many thousands of sensors in use. How to calculate water balance on a trunk main. So, Martin.
Yeah, okay. Really, it's all a question of measurement. You would really need to know what your flow was going into your trunk main and what your flow is going out of your trunk main, and then you subtract any exports in between the two. And the remainder is going to be your losses, whether it's apparent losses from illegal tappings or whether it's real losses from leaks. So the key to trunk main water balances are flow meters. And then we start talking about accuracy of the large flow meters and calibration and all the other factors that go with it, which is something that does require consideration when you're running it. But to answer the question, it's all about metering. How many leaks do we capture between two hydrophones based on pilot project at Selangor? Can it capture 5 leaks in one correlation reading? I think Matthew has mentioned previously that in order to do a correlation, you need to be able to detect the acoustic energy at both hydrophones. And because in Selangor, on average, we're over 3 kilometers apart, it's very unusual for the acoustic energy from a leak to travel a large distance to be able to be detected by both sensors. So for IS Selangor, it's not what I would expect to happen. But can hydrophones pick up 5 leaks in one correlation? The answer is yes, they can. Assuming that all your data is perfect, as long as you've got good GIS, the leaks are the leak noise is clear. It is possible to detect multiple leaks in one correlation. Okay. And I think we're there.
Yep, that's all the questions I see.
Okay, so I'll take it over. Can you hear me?
Yeah. Well, yours, Denise.
Thank you. Thank you, Datuk Kadir and the Malaysian Water Association for hosting today's webinar. Thank you, Martin and Matthew, for your invaluable contribution to our participants. Thank you for your time in preparing your presentation. Last but not least, thank you everyone for joining us. Next week, we will not be having any webinars since we're having the Hari Raya celebrations. We will have the next one on the 2nd of June at 3 p.m. But please get updates from our Facebook in case the time change. So the next webinar will be on groundwater, presented by Niras and Ognet Water Technologies. Our speakers will be Mr. Michael Jorgensen and Mr. Berger Christian Blem from Denmark. So do follow us on our Facebook, Malaysia International Water Convention. And on our Facebook, you will also get the link to watch today's video again. To all our Muslim water industry professionals and friends, we would like to wish you Selamat Hari Raya. Thank you, everyone, and have a nice week ahead. And we will see you again on the 2nd of June. Thank you, Dato. Thank you, Matthew. Thank you, Martin. Thank you, everyone. See you
Okay.
again. Selamat Hari Raya.
Thank you,
Thanks
Denny.
all.
Thank you,
Selamat Hari
so
Raya.
all the
Thank
best.
you.
Thank you for the participation. Thank you.
Yeah.
See you
Thank
next.
you to all our participants.
Yep. Thank you.
Thank you. Bye.
Thank you, everyone. Bye-bye.
Bye.